This week we have a big and important topic of concurrency. There is a lot of stuff to cover here, but this first video we look at the central terminology and the idea and the motivation, and then the next videos are gonna show these techniques in practice. So let's get this theory and terminology part out of the way again so that we can get to the interesting stuff. So far all our code execution has been sequential, like you think of a single method. The method consists of statements, and the compiler turns those statements into low-level bytecode instructions, and then the Java virtual machine, one of the processes running inside your computer, and theoretically just like of any program, so you could launch any number of processes at the same time. So then the virtual machine simulated processor executes the bytecode instructions one at a time, and the effects of the instructions modify the contents of the stack and the heap. So program, a big thing, consists of small steps executed in sequence. But the idea of the concurrency, that if some of the steps are independent of each other and they don't interfere with each other and they don't need each other's results to proceed. So realization that the strict sequential fashion is not necessary. We could change the order of those two steps without affecting the end result. It might affect the intermediate results, but those don't show up anyway. As long as the end results are correct, so then compiler is free to rearrange the execution of your program any which way it pleases. Parallelism then is the furthermore realization that these, if the steps are independent of each other, they can be executed physically simultaneously. So these days we got multi-core processors, and Java, simply by doing this concurrency and leaving the details of which processor core is doing what at any given time, you don't know and you don't care. Virtual machine's job is to do all that kind of scheduling and optimization. So you just write your code in Java, and then when you write it in this kind of a fashion, you automatically get the benefits of the parallelism. So even in an old-timey single processor machine, concurrency can still be a good thing to make the program clearer. Analogy to the data. So we have so far we've been creating different data types. Different data types offer different functionality and contain different data inside them. So why don't we just make one data type that everything would be special case of? So of course that would be horrendously complicated, and then it would be far less flexible, and it's much better to break down the data, even though all the data is all there together in the memory as a bunch of bytes, to break it down into smaller pieces that can be understood and manipulated on their own. So analogy to this, that we could write any program as a single-threaded sequential program, but the parts of the execution that are independent of each other and can be understood on their own, we might as well split the execution into multiple concurrent execution threads. And this way we can just examine each execution thread on its own, and then as long as the interaction of that execution thread with the other execution threads is localized and simple enough, so then this makes it far easier for us to organize the execution of the program. So the same way that the types and the classes and objects are the way to organize the data at the runtime, so concurrency is the way to organize execution into smaller pieces. So Java virtual machine program that executes the bytecode instructions, it's like any other program. It's no different in any fundamental fashion, and it's one of the processes, like this web browser is one process, probably way more. And then the photo booth here is one process, and the operating system has a bunch. And so a virtual machine, you just launch a program, and you could even launch multiple processes. Each one is a Java virtual machine. Then they would all be separate. For example, the static fields, they would be completely separate. Now, important also, if we don't do concurrent programming, we gotta understand couple of things that we've seen before, that all the objects, they reside in the memory area called the heap, and then the local variables of the methods are stored in a stack, and these have very different lifetimes as you recall. The object that you create in a heap continues to exist as long as it is potentially reachable from the live variables of your program, whereas the local variable, the stack frame, is created at every method call and then erased from top of the stack when the method returns. Slight oversimplification, but simple enough for now. So then the program itself, the bytecode statements, they're completely separate memory area, and then the Java virtual machine, for safety and security reasons, your bytecode instructions can modify the contents of the stack and the heap, but there is no way to create a self-modifying program in Java, because that would be just a horrendous safety and security hole, especially in a language that was intended that anybody can go to a web page and then whole bunch of Java programs, applets are automatically come along with the web page, they start running in your computer, and how can you even go to the seediest corners of the World Wide Web, so how can you still be safe in principle? Because the Java virtual machine, it creates basically a virtual simulated computer inside your real one, the same way like you know that when you're reading some novel like Harry Potter or something, so then you are in your mind simulating the virtual world, but you know that you can do this completely safely, because even if the book suddenly says that suddenly the whole world exploded, so then just happens only in the simulated world inside your mind, the rest of the reality is unaffected. Now of course we realize again in the spirit of disconnected times that the programs can reach out and touch someone to the out. So what is this dividing line? It doesn't always necessarily hold. And even a program running in a virtual sandbox, so if it manages to make the human do something, so then it has again reached out of its bounds. But that's a topic for a different course. For practical purposes here, so what we gotta understand, so for when we do concurrent programming, that we have multiple execution threads executing at the same time. So what happens in Java is that there is exactly one object heap. All the objects reside in the same heap, even if they are created by different execution threads. And this way in Java, so actually how these threads communicate with each other is that they communicate by changing the values of the data fields inside the objects. Every thread, because the execution of the threads doesn't have to proceed in lockstep, each thread can be executing whatever part of the program the past has happened to brought it in. So then the threads in general are executing different methods, and they have a different history, the stack trace of how they got to those methods. So necessarily each thread must have its own stack. So the local variables, they don't show to the outside of the thread. But the one object heap then the objects, by using the shared objects and using those objects to store data, so like a secret agent, the dead drop of some kind, one leaves a message somewhere and the other guy goes to see it. So then this is the way that the threads communicate in Java. And what happens, this execution model, when you start the Java virtual machine, so what happens is that the main thread, aptly named because it starts running from the main method of your program. So the main method is no different from other methods, it is just the default starting point. But when you write the main method then in BlueJ, so BlueJ itself is written in Java, it has had its own main method. So when in BlueJ you then interactively call the main method of some class that you wrote. So BlueJ is just creating a new thread and then executing the method call there. So the main thread of the Java virtual machine running Python is running BlueJ, and then your program is just one of the other threads. But the main thread, so that's just the name. So main thread is not any magical, it is a thread like any other. And then the second thread that starts running right from the start is the garbage collector, a low priority daemon thread. So thread has an extra bit whether it's a daemon or not. So daemons, so nothing nefarious there, it just means a background work. And the idea is that once only daemon threads remain, so all the other threads including the main thread have terminated, so that's when the virtual machine itself knows to set up the shop. So now in our normal programming, so you run your Java program, the main thread is the only thread that you have. So that means that when your main method terminates, a thread terminates. When its starting point top level method call terminates, so then the virtual machine process itself begins. So we gotta be careful. One last thing before I end this video is that when you create your own execution threads, you gotta make sure that they will terminate. Otherwise, your JVM process can never terminate. Then you just have the process running there forever until you explicitly terminate it.